Okay, in this video I'm going to demonstrate how to graph tangent functions. And so we're going to take a look at those. And first thing is the general template of a tangent function is very similar to our other templates that we've looked at. The only thing that is missing on this template is possible vertical shift plus D. But because, as you can read here, because the remaining trig functions are all defined as fractions, then they're all rational functions which have the potential to be have undefined values. And as a result of that, we are going to have asymptotes in these curves. They are not going to be wave-like due to this fact. And so let's just take a look at the tangent ratio. We know that the tangent ratio is equivalent to sine x over cosine x. And so as a result of that, wherever the cosine x is equal to 0, that's where we're going to have an asymptote. So as we look at this red graph right here, we can see that we have asymptotes where we have every 0 of that function. Those two asymptotes that are closest to the origin are at negative pi over 2 and pi over 2. So as we look at these patterns, we will see that for a parent graph of the tangent function, that there will be an asymptote at every odd integer of pi over 2. Say, for example, 1 pi over 2, 3 pi over 2, 5 pi over 2, and so on and so forth. But it can also go in the negative direction as well. The period of the tangent function is actually pi, not 2 pi, due to this fact. Because for every sine curve, you have 2 zeros. And so that's going to cut the graph in half. And so the period has been cut in half too. The tangent function will also have zeros at the zeros of sine. Again, if you were to take a look at the sine curve and or the unit circle, if sine is 0, then tangent is going to equal 0 because anything 0 divided by anything is going to equal 0. And these roots, again, will occur at all values of pi times an integer, such as 1 pi, 2 pi, 3 pi, and so on and so forth. These zeros also are exactly halfway in between the two vertical asymptotes. And so you can kind of see that right there. It's halfway in between those two vertical asymptotes. If we take a look at the values, the table of values, you'll see where those asymptotes occur right here at these error points, and that's at negative pi over 2 and positive pi over 2. And I know you may not get this joke right here, but haha. At any rate, the parent graph, again, there's the parent graph. It does straddle the y-axis. Obviously, there's other parts of this cycle that we could say is the tangent curve, but this is known as the parent graph, the one that's closest to the origin. And let's talk about the fact that the tangent curve will not have an amplitude. Amplitude, we know, is the max and min of the curve, but as you can see, that this is a rational function. It has no floor or ceiling, so to speak, and so therefore its range is negative infinity to positive infinity. Therefore, that would be the reason why we wouldn't have an amplitude. However, there are numbers that can take the place of the value a, and these will affect basically how quickly the graph grows and the direction. It might be a reflection over the x-axis. So again, we see that the tangent curve behaves like a rational function. Okay, so in a nutshell here, everything that I just said is true. The parent graph will have vertical asymptotes. It doesn't have an amplitude, and so on and so forth. But as long as you know your sine and cosine curves, you can always figure out the tangent curve if you have to. But there are some shortcuts that I'm going to actually show you as well. This is one of them. The LA stands for left asymptote, and left asymptote can be found by letting the bx plus c part equal negative pi over 2, and the right asymptote can be found by, in like manner, the right asymptote pi over 2. So we can use that little shortcut rather than sketching the cosine curve, which is often done. So let's take a look at this first example. First of all, it's negative, and so that's the value of A. In other words, it's going to be a reflection. So instead of going up to the right, it's going to go up to the left. And so to find those asymptotes, once again, we let the bx plus c, which is this part right here, we set it equal to negative pi over 2 and solve for the left asymptote. And again, it's negative pi over 2 because in the parent function, that's where the left asymptote is. The right asymptote can be found by setting it equal to pi over 2. And the reason this is switched is because the value of b is actually 1/2, and so that stretched the period to 2 pi. And as noted, the range is always going to be from negative infinity to positive infinity. And this part is, you're going to have a domain is going to be at negative pi plus 2 pi k, where k is an integer. Now the 2 pi comes from the period, so we could actually replace that 2 pi with a generic word, the period times k. There's other ways of stating that as well, as we'll see further on in this demonstration. So now what we need to do is just find the halfway point. As we mentioned before, you can see these red circles that I've made, the dots. The other 2 dots I want to talk to you about a minute are the halfway points between the left asymptote in the center and the right asymptote in the center. And you'll notice that I plotted them up at 2. And the reason being is because the tangent of 45 degrees is 1, and that's something that you need to commit to memory. In other words, tangent of pi over 4 is equal to 1. So when you have, if you take and put this negative pi over 2 in that position, you take half of negative pi over 2, you get negative pi over 4. So that's 45 degrees. So the tangent of 45 degrees, you know, is 1. So when you multiply that by the negative 2, you get negative 2. So that's the exact reason why this is going to be up here at 2. And again, that negative just simply means it's the reflection. So in like manner, that's why this other point over here is going to be down at 2. It's not going to be drawn as a straight line. We're actually going to make it look like more of a cubic function, but it behaves towards the asymptote as what usual rational functions do. Okay, we can do other half curves there as well. It's not always necessary, but it's sometimes seen. All right, let's take a look at this one. The value of A is 1, so we know that it's going to be have a period, or excuse me, it's going to be in other words, there's not going to be a reflection. And the period is also, the value of B is also 1, and so the period is pi over 1, or pi. So it's going to emulate the parent graph quite a bit. The value of C, now there is a horizontal shift here to the left of pi over 2. And so as we look at our procedures, we want to just find the left asymptote again, take that portion right here, bx plus c, and set it equal to the left asymptote, which was negative pi over 2, and solve. And if we continue to go through each step, we find the right asymptote, we sketch those asymptotes, we find the points halfway in between, and since these graphs are not a reflection, then our halfway or midway points will be at 1 again, because that's the value of A. And then we can draw as many cycles as we need to. One is usually enough, but in this case I drew several just so you get the picture. No pun intended. Haha. Alright, so let's take a look at this next curve. I'm going to back this up a minute. Alright, so again we're going to try and find the left asymptote and construct it. And then the right asymptote is going to be pi units down the road. We can do it this way, or we can set that equal to positive pi over 2. You get the same thing. And so there's the period of the graph between those two asymptotes. You can draw other asymptotes if need be. Again, you find your zero of the function halfway in between, and then the two other midway points would be at 1 because the value of a is 1. And then you just sketch the graph. And again, you can do multiple cycles. Again, the important thing is that you place those asymptotes where they belong. Alright, this one's just the reflection of that, so it's going to be very, very similar. It'll have the same exact asymptotes as the other one, except for this time it's going to be going in the other direction because it's a reflection graph. Alright, and then finally, we take a look at this one. Once again, we want to take a look at the period, which is going to be 4 pi. So our asymptotes are going to be 4 pi units apart. The left asymptote, we again set equal to negative pi over 2, and therefore that left asymptote is at negative 2 pi, and the right asymptote is at 2 pi. And the value of a is 1, so again those midway points, these 2 points right here, are going to be at 1 and negative 1. And then you just can sketch your curve. That's good enough. I hope this has helped your understanding of tangent. In the next video I'm going to talk about the cotangent.